So this is going to be about what this community of data science, big data, data mining that has revolutionized the way we do commerce, live our daily life, entertain ourselves, elect presidents, and so forth. What could it do for the world of climate? And the domain of climate, like most other domains, used to be extremely data poor. But a slow transition started happening about 50 years ago with the advent of satellites, and then with faster computers and more sophisticated models, you see a simulation, a realistic simulation of Earth systems model on the top left of an NCAR. There's a massive amount of data being generated, literally petabytes of data generated on a sort of a daily or weekly basis, and leading to exabytes and beyond. And as a result, there is a great realization in the climate science community itself that they of course have always been working with data for all the time, but they realize that the climate research has become big science comparable in magnitude, complexity, and importance to human genomics and bioinformatics, which went through the same transition starting about 30 years ago. So this is beginning to happen very, very rapidly now. That what it means really is that this community really needs the help of all of the different techniques that we are able to bring to bear on a wide variety of problems. So I am part of this project on understanding climate change using data science approaches. And this project, of course, involves half the team is a computer scientist, half the team is people from other disciplines, Northeastern, NC State, Northwestern, and others. And the objective of this project is to see what are the different techniques in data sciences that we bring to bear to really impact some of these climate science applications. And this slide is just to give you a very, very broad overview of different things that are going on. On the top left, you see the study of the oceans using the ocean altimetry data, the satellite altimetry data for the last multi-decades to study the dynamics of the ocean's currents and eddies. The top middle part is showing you how the climate systems can be converted into a network, and then eventually could be analyzed just like any social network. And the techniques that you develop to find teleconnections and relationships then can be applied to other data sets like the brain fMRI data sets. You heard some of those talks yesterday in yesterday's keynote. And then sort of course, the list goes on. I'm just going to talk about today on one of these topics of change detection using satellite data, looking at the land surface changes, which is the middle bottom circle here, and I'll have something more to say about it. But from this very wide range of problems that you see here, one thing that's common is they have lots of data. We talked about that, right? And we sort of say, well, we must be ripe to address these challenges. But the big problem is that the data sets that we have to deal with in these domains are substantially different than the kinds of data set that we are used to in our community, because these data sets about the observation of a physical phenomena, which is often sensed and observed at multiple resolutions and multiple scales, from sensors that are embedded either in the space, which are sort of doing a graded data set, or could be sensors, or could be balloons, could be buoys in the oceans. So there is a huge difference in the way we look at the data and when you're dealing with customers and the social networks and so forth, as opposed to in the climate domain. There's a huge amount of variability. Of course, variability exists in any phenomena. We're not in this community unaware of this, but the amount of variability and at different time scale that it happens, like in weather, there are seasonal variations, there are daily variations, and there are decadal variations, and they all combine. And the phenomena that you're trying to understand could be the predictive model that you're trying to build. The relationships may be very different in different locations on the Earth and during different times. So there's a spatial and temporal heterogeneity, which makes the job very, very complex. And as usual, because of the way these data sets are collected, there's often a lot of noise and missing values, clouds, and all sorts of issues. And lots of data, but very little ground truth. And the phenomena of interest is, of course, very rare. So these are sort of all of the issues that, of course, both make it very challenging and also very interesting. Within the process of addressing these challenges, then we are forced to develop new techniques, but then those techniques, those methods are not limited only to climate. They can go and be applicable elsewhere. So as I promised you, I will, rather than talking about the entire giant problem, I'm going to focus on one subset of it, which is the Earth being observed from the satellite, from the space, using the Earth, using instruments that are sort of providing a wall-to-wall coverage of the Earth on a temporal and then spatial basis. So what you're seeing here is in the animation is the animation of a MODIS instrument, which takes picture of every single location on the Earth every single day. Okay? It's a very coarse picture. A square kilometer has about 16 pixels. Okay? And this data set happens to be available for the last 17 years, starting in February 2000, available to the entire world free of charge. And this is just one example. Landsat, which actually went up 40 years ago, but its data set became available only recently, is much finer spatial resolution, and but not as good temporal resolution. And that's available. Europeans have launched a very high quality satellite, Sentinel series of Sentinel-1, Sentinel-2, and more coming, that provide even finer resolution data set at 10-meter resolution, again, weekly or 5-day coverage of the globe. And then there are all sorts of smaller projects have come up in which people would sort of launch CubeSats, satellites of this size, or literally throw them in the sky, and they will run around for about a year and then provide very high quality pictures. And so there are all sorts of data sets available. Now, the size of these data sets can be very, very large. Just at 10-meter resolution, and Sentinel, for example, would be about 1 trillion pixels for the entire globe. And each pixel, you're collecting about a dozen different variables. So this sort of tells you that there's a lot of data. You can collect this data into spatial mosaic that you're seeing here, or a temporal time series at any location. And it offers a whole bunch of opportunities. And I'm just going to talk about I'm just going to highlight 3 different examples, of which the first 2 I'll just talk very, very briefly and try to give you a little bit more detailed presentation on the third item. So the first, and again, in each one of them, I'll try to emphasize the challenges that are faced in addressing these problems, the novel methodologies that got developed, and the implications of those novel methodologies in broader data science. So one of the first problem is being able to map the forest fires. Why is this important? Because the population is increasing. We have 7 billion people now, will be about 11 billion people not too far into the future. The food needs are going to go up. We need more food, but we have less land. We can't really, and what's happening right now is a lot of these forests are being converted, especially in the tropical area. They're being burned and converted into plantations, and to be able to monitor those and make sure that those destruction of forests doesn't happen, we need to be able to monitor these forest fires in tropics, which is a very hard thing to do, and being able to sort of map which of these locations are being converted into plantations, because most of the world's largest corporations have promised not to buy products that come from the supply chain that leads to these forests that are destructed. But then they really need to know where their products are coming from. And all of this involves solving this problem 1 and 2. Okay? Now, solving the problem number 1 happened to lead to an entirely new formulation in which you build a predictive model and you don't have ground truth of the kind that we're used to. Okay? And I'll very, very briefly talk about that. And why why were we forced to develop a model like this? Because there is such a heterogeneity in different parts of the world that if you try to build a relationship between what you see in the spectral space and whether this area was burned or not, this relationship changes dramatically over different locations. If you build a map for California, it won't work in Halifax, for example. If you build in North America, it definitely won't work in Africa or Indonesia. The phenomena that you're trying to observe is highly imbalanced. Most of the forests mostly remain intact. Only a few of them are burned. And So all of these challenges that sort of come together make it very, very interesting and very difficult to solve this problem. And it took us about 7 years to crack this in a very satisfactory way. And we had to sort of use a phenomena that is for these problems, even though the gold standard ground truth are not available, but poor quality labels are available for every sample in terms of other variables that can be collected to satellite, for example, the thermal anomalies. And using that, it becomes possible, and a whole bunch of innovations that have been done in this community, in data science community, going back 20 years. Many of them built in the context of working with imperfect labels in annotations using the mechanical Turks and so forth. And that sort of led to a formalism which now is able to build very accurate maps of forest fires in the tropics, like in the Amazon and in Indonesia, and is far superior in quality and coverage to the state-of-the-art product. The second thing I talked to you about was the mapping of plantation dynamics in tropical forests, because these forests are burned and then eventually they're converted into plantation in many cases. And the phenomena here happens to be something that's not a discrete phenomena. Fires can still be considered more of a discrete phenomena. The forest was intact and it got burned. Now, in the plantations, you plant the trees and then they slowly grow over and eventually they look like forests. So you have to sort of capture the entire process, and it turns out that some of these deep learning methods with substantial extension to include spatial information and other aspects were very powerful in handling this problem. And especially the problems that sort of exist here is that the ground truth that exists in this, given the importance of this problem, there are a lot of international organizations who are trying to build maps of what areas are plantation and what areas are not. So for example, there's an organization called Transparent World, which has a map in 2014, one year map, but it happens to be highly inaccurate. And there's another organization called RSPO, which has a map, but only for a couple of years, and that happens to be very incomplete, a little bit more accurate. So using these new methodologies, now we're able to build the entire South Asia maps of the plantation dynamics. If you look at this picture very closely, you will see that the red areas were the plantation as of 2000, and each year after that, 2001, 2002, the right now 4, 5, you see how the plantation have been growing, and then you have a very precise idea as to which of these plantations were grown, built in which year, and which were, using the previous project, you can sort of figure out which of them were burned, and which of them were burned and caused collateral damage. So all sorts of questions can be answered that are very, very important. So again, these two sort of are examples of that you can handle these challenges and in turn come up with very interesting algorithms that have a much wider applicability. In the case of these RNNs for monitoring the forest plantation dynamics, now extended version of these ones are being used to now map crops at 10-meter resolution using sentinel data and providing much better quality results than anything else that could be obtained. Now, let me just talk about a third case study, which I'm going to spend a lot more time on, which is being able to map the dynamics of surface water. Now, mapping of, and of course, this resulted in a whole bunch of new innovations, things like ensemble learning that can deal with heterogeneous data, physics-guided learning, I'll talk to you about a little bit, and a very interesting concept about how do you transfer information across space and time, because these phenomena are observed at different spatial and temporal resolution, and is there a methodology that you can sort of leverage multiple types of data to get better results. So why is the monitoring of water important? Because of course, you know, we as a humanity cannot survive without water, and our actions sort of impact the availability of water. You see Aral Sea in 1960s, and it was 1960s. It was a big, giant lake, the largest lake in Asia, and now, and more recently, it has become a tiny sliver. On the top, on the bottom, on the left side, you see Sido Sika Lake in Tibet in 1984, a frozen lake. In 2011, it's all melted water. So basically human actions and climate change is impacting water supplies. And one of the biggest, perhaps the first major impact humanity would see of climate change would be through water in many, many different forms. So being able to understand what's happening to water, the water cycle, the flow and stocks is extremely important. And it turns out that for this problem, one could sort of say that we have a massive data set available for training, because in February of 2000, given the importance of this problem, the NASA launched a special mission of the space shuttle just to map water. So for one date, we have a reasonably good, it's not a perfect map, but a reasonably good map of the entire globe of where the water was, except that it tells you on one date what happened, right? You need the dynamics. But you could sort of potentially use this as a starting point to build a predictive model, except that as you build these models, you have to worry about a whole bunch of things. And one of them is, just like anything in nature and in the climate and ecosystem domain, there's a huge amount of heterogeneity in space and time. So what you're seeing here in these pictures are the multispectral composites. So this is like saying you have the multiple spectral data, multiple spectral bands, you map them to red, green, blue, and then you can see them. Right? So all of these pictures are built using only one mapping. So the colors sort of tell you how heterogeneous things are. So you can see even in a small region of Africa, one continent, you can see multiple lakes, and each of them looking very different in terms of water and land. I mean, visually when you see it, you know where is water and where is land, right? The darker portions are water. And you can sort of see that they all look different in the spectral space. That is, there is no one region of this multidimensional space which is, hey, this is water and this is land. And then the lower portion is showing that even at the same location in Argentina, same lake, on 2 different days, it could look very, very different. And then you add to that all sorts of other issues like the clouds and the noise and then the mountain shadows and all sorts of things, and the algae in the ocean, in the lakes. It becomes a very, very difficult problem. And the other problem is the data quality. When you're collecting stuff on the satellite, from the satellite, things are very hard to see. And I was giving this talk in Beijing, so I picked up this Poyang Lake from China, which supplies fresh water for the city of Beijing. And anytime you see the red color, which means data is not there. Okay? And if you see this movie, most of the time data is not there. So the question is, how do you work in situations like these? Now this, to begin with, might seem like a challenge, but sort of say this is an impossible problem to solve. Let's move on to something more easy to work with. But then struggling with this and trying to figure out how do you really solve this problem can actually lead to many, many interesting solutions. And being able to deal with the heterogeneity aspect led to novel solutions for dealing with heterogeneous subgroups. You know, again, papers in different conferences in this field. But then these methods are also being used in healthcare now to figure out how do you build models that will be applicable to only different subsets of the population. So this is one innovation in ensemble learning method of heterogeneity. The other one, which actually is almost like a gift that keeps on giving, and I'll talk about it a little bit more, is something that sort of come across in any of these scientific domains where something that we don't use in this community becomes extremely important, and which is typically we work with the data, you give me the labels, I'll build a model. But there's a massive amount of information about the domain that can be very, very useful. And in this particular case, one thing that we know is that water bodies happen to form in cavities, in the physically relevant cavities, which means if a location A was labeled as water and location B was labeled as land, then you know there's something wrong. Okay? Now, this is, of course, a trivial observation, a very high-level observation. And if this elevation information was available perfectly, I could use it to improve any classification algorithm. But it turns out that on a global scale, either the information is not available at the right resolution or it's of very poor quality. So the biggest challenge becomes one of how do you use this insight without having the elevation data? So this is sort of, there's a physics, but I don't know it. Okay? So this is like implicit information about elevation needs to be used to figure out how do you make these corrections. And how do you transfer information across space and time? And these collection of ideas pursued actually have allowed us to build a system. If you're sitting in the audience, you can go to this link and type it on your iPad or your laptop, and you will be able to now see the dynamics of the entire globe for surface water at a level that has never been made possible before, right? And of course, the system is public, anybody can see it. There's always several months behind our latest results. So it won't have all the things that I'm going to talk about, but it has, you will be able to sort of see many things just by going to this. It basically maps dynamics of all major surface water bodies that are at least 10 pixels large, and at modest 500-meter resolution, that means about 2.5 square kilometer, and which means about literally tens of thousands of water bodies that you can see. You can find I gave you one example of melting glacial lakes in Tibet. You can find all of them. Okay, rivers change course, and rivers change course because the silt sort of flows through as you deforest the trees in the tropics. The silt sort of goes to the rivers, and then they end up changing their courses. A lot of focus on building hydropower dams in response to our actions that we sort of wanted to build renewable energy, right? The energy for water was supposed to be the cleanest and the best. It turns out it has huge ecological impact, negative impact. In the US, all the dams are being converted back to broken, and rivers are being decommissioned. Hydrologists want to study what these dams are, where they are, and what the impact they have. Using the system, and I'll show you, you sort of have a global picture of what's happening in the last 17 years. And the sort of the list goes on. And I'm just going to, since I just have a few minutes, I'm just going to show you very quickly a few examples to give you a sense of what the systems looks like. If you went in and you clicked on a certain tile, the circles will show up. And if you sort of click on one of those, this happens to be the Don Martin Dam in Mexico. The system would allow you to sort of tell you how large this surface water body has been in different times, going back to 2000. And you can sort of see this body was 400 pixels in the beginning of 2000, then it shrank, then it became big, then it shrank, became big, and so forth. This just happens to be normal variation. How do you know this is really good? You can see pictures on Google time-lapse. So the system would let you see the time-lapse images wherever it's available. And you can see that this image is sort of dancing around in the same way as you see in the time series. You can color these dots in terms of whether they are increasing or decreasing in the last 17 years. In this picture, the greens are shrinking and reds are increasing. You can see the examples there. And then you can see a whole bunch of location in vast area of South America and Argentina. Everything is green, okay? Very suspicious. Well, this area had a lot of water back in 2000, 2003, but lately it has very little water. And every single location in there, every single water body has this phenomena. That is, you look at anything, it sort of grew until 2002, and then it shrank very rapidly. It happens to be a farming area. There must have been some interaction between the human actions, farming, and the water supply there. I talked about Tibet. When you look at the system and you come to Tibet, you will see all these red dots, all water bodies increasing. Okay? And if you zoom into this, it will sort of give you the little areas which are specifically the area that increased over the last 17 years. You see another area that increased here. And you can, again, go to time lapse, and then you see all of these changing over a period of time. And if you look at the last 17-year period, the total amount of new water that has shown up is of the order of 8,000 square kilometer. New water bodies have showed up in Tibet. Now, this area supplies water to rivers that feed about 2 billion people on the planet. So this is a very, very sensitive area. So any implications of climate change to this area are very, very serious. And before this, people would study these lakes on one date at a time. That is, so somebody would go to one area and use satellite images and sort of say, well, I have a map of this area, how these lakes look like on a single day. Now you have a continuous coverage of everything. You can see river meandering, for example, whenever you see the red and green dots nearby, you see rivers meandering, and then you can see them. And again, all of this is available on the system. So I'm just giving you examples that you would be able to see on your own. You can see islands shrinking in response to rising oceans. So you see the little blue area on the surface of a small island of South America. This is the area that got shaved off in the last 17 years. Now I'm hoping that this time-lapse image, okay, now time-lapse image for this one is not working for some reason. But on the system, you may be able to see this little island, and if you, on the system, you'll be able to see the island shrinking even from Google time-lapse. You can see, I sort of told you that you can see the construction of dams. I was giving this talk in Tokyo, and I sort of said, look, here is a dam that was built in 2006. And of course, you can see that because there's a water body that wasn't there before 2006, and it came back to something bigger. But the major utility of this is that the hydrologists who study these dams all over the world, they have a database called GRAND, Global Reservoir and Dam Database. It was built in late 1990s. It was pretty accurate until then, and after that, it has simply relied upon people reporting when the dams are built. And these are the dams that are reported all over the world for the last 17 years. This is what our system finds. Of course, you find all the usual suspects: China, India, Brazil, Middle East. A lot of these places have built a lot of these dams. But what I'm saying is that you have this thing that's available to hydrologists for very, very quickly. So all of this is actually now leading to a point where we can really provide a lot of actionable information. So I'm just going to talk about two major actionable information that this project is sort of beginning to lead to. And one of them is there's a great interest from the international community in trying to figure out how much water we have stored in the reservoirs around the globe and how these water supplies have been changing. Water storage has been changing over the last decades, several decades, in response to climate change. Okay? Now, we have the surface area for all of the water bodies that are large. For many of them, we have the altimeter data from the satellites, and combining the two, we are able to provide this information, and which is called one of the essential climate variable, and our group is responsible for providing this. Okay? The second thing that's extremely important is being able to measure the flow of water across rivers, because rivers tend to run through different countries. And there are agreements on as to how much water you're supposed to use and how not supposed to use, and how the water supply may be changing. And countries are very, very protective of that data. Okay? Even within a country, different states will not share information about how the water is going across. Now, what this system effectively allows is being able to construct that information on an automatic basis on a global scale. And it's not direct. There are a few other steps that are needed, and those steps are needed for the third point as well. And the third point talks about being able to calibrate hydrological models. Now, hydrological model may seem something very, very fancy or technical term to you, but there's a national water model that's being constructed in the US, which is supposed to predict the stream flow for about 2.5 million locations for the entire country. And the idea is that wherever you live, there could be a flood, there could be shortage of water if you're a farmer and you really need to know what it is. And that model is going to be calibrated using data only from about 4,000 locations. And given the heterogeneity in the space, people are worried that this model would actually do extremely poorly, because the world is far more heterogeneous to be captured by 4,000 locations when you're trying to predict 2.5 million locations. So you need much more validation data, and it turns out that by being able to provide very precise estimates of surface water and how it's changing, we can solve that problem. Okay? But for the last two examples, what is really needed is much higher resolution maps of surface water. What I showed you and what you will have on the system is maps at modest resolution, but 500-meter resolution, and those effectively are at daily scale. But actually, they're effectively at 8-day scale, because daily data is very, very noisy. Now, what we want is a much finer resolution maps, and hopefully on a daily scale, and that requires being able to transfer information across space and time. And again, I have only about a minute, I assume, so I won't really try to go into the details of this, but a series of technologies, series of methods got built to transfer this information across space and time that make use of the physical notion that I talked to you earlier, and that has resulted into, I'm just giving an illustration of a very preliminary version, and what you're seeing here is a reservoir in Afghanistan, a Kazakai reservoir, it's a big reservoir, and you see on the date on the top, July 24th, 25th, 26th, it's a daily observation that you're seeing for about 2 weeks. And on the left side, you're seeing its picture constructed at the modest scale. Modest scale means each square kilometer got broken into 4 pixels. So they're pretty large pixels, right? They're square pixels. And on the right side, you're seeing a very, very fine image of the same reservoir being constructed, right? All done using this information transfer scheme that I have just barely mentioned to you and not told you about, right? So one thing that you can sort of see is that the right image is very fine grained. Of course, you don't know whether it's any good, yeah, because I could just show you anything, right? So to make sure that I'm not showing you something that's irrelevant, I'm going to show you the image for one date for which Landsat information is available. Okay? So this is the date. What you see on the underground, what you see in the background is the image from Landsat satellite, Landsat sensor. which is at 30-meter resolution, very fine resolution. So you can see when you look at the Landsat sensor, you can see the black areas are water, and then the non-black areas are land. And you can see on the left picture, the MODIS is grossly simplifying the image, because if you look at this bottom part right here, it's taking this entire area and calling it a single line, as opposed to looking at these fingers that are sort of protruding, right? Now, if you look at the right image, which was constructed using this information transfer scheme without looking at the Landsat data, you can see that it matches Landsat image much, much more carefully. So this is the kind of thing that I'm talking about, new innovations that can be brought back to much wider range of applications. I'm out of time, so I guess this is going to be my last slide. Okay? That I hope I've convinced you that big data in climate offers great opportunity to advance our understanding of Earth's climate, very important for society, but it also offers opportunity to advance our field, because each one of these techniques that are developed here then have much wider applications. And the other message, again, coming from this sort of experience and many, many others that I like to sort of be able to share, is that in many of these scientific domains, there is a lot of knowledge that exists about the applications and the physical phenomena, and we need new methods to bring them into these new techniques, new approaches to bring them into data science approaches. And of course, once you do that, hopefully they'll be applicable in much wider set of domains. So with that, thank you for your attention.